Good morning. My name is Erez, and I would like to tell you about my research with Professor David Kessler and Professor Eli Barkai about infinite-covariant density for fat-tailed systems. Now, for those of you who were not here, last week Eli Barkai gave a related talk, and I will just briefly mention some of the things he discussed, but I recommend you would watch this talk online. My talk is about fat-tailed systems. Now, in a fin-tailed systems, you know that the probability density for the particle's position falls off very quickly, exponentially quickly at the tails. So you all know, for example, the Brownian particle, the final position particle, which starts at some initial location x naught. This probability for its last position is given by the normal distribution. This is the result of the Gaussian central limit theorem. Now, in a fat-tailed system, the actual decay at the tails of the probability density is a power law, which is much slower than an exponential decay. For example, take a look at this Levy flight process. A Levy flight process is dominated by rare events where you have very large jumps, and they take over the whole the probability density for the final position of the particle. Here, the final position of the particle is given by the Levy generalized central limit theorem, and the Levy distribution here, it has power law heavy tails, which are so heavy, in fact, that the variance of the process is expected to diverge. But, of course, a diverging variance in a diffusion process is not something which is so physical, because it means that a particle will reach infinitely far at a finite time, and this does not occur. In a real physical system, Levy flight is not so physical. In a real physical system, what will happen is that these power law tails, they will be cut off by a different function, and here the actual large fluctuations of the density will be described by an infinite-covariant density function. And this you will understand by the end of my talk, I hope, that this function somehow reminds the rate function in large deviations theory, but it's very different in almost every other aspect. So the motivation and the example that I'm going to discuss here is a physical model which describes the diffusion of laser-cooled atoms in a process called Sisyphus laser cooling, for which it is a very known model for which Cohen Tanuji and collaborators received the Nobel Prize in 1997. And we first started looking at the large fluctuations of this diffusion after this experiment by the group of Sagi and Al from Weizmann Institute. They had conducted an experiment where they showed that the probability density is in fact heavy-tailed. So, in stochastic terms, the diffusion of the laser-cooled atoms can be described by the pair of Langevin equations here, one for the momentum of the particle, p, and one for the position of the particle, x. And I will discuss how we study the large fluctuations of the position distribution. Now, you can see that the momentum distribution, the momentum dynamics is actually controlled by two competing forces. F of p is the deterministic damping force, which is created by the lasers when the atom is traveling inside the laser fields. And this deterministic damping force is responsible for taking the momentum down and for cooling the particle. But you can see, as you can see, it has a very anomalous shape, where if you are cold enough, if your momentum is small enough, then f of p is proportional to minus p, like normal Stokes friction. But actually, if p is very large, then f will decay like minus 1 over p. So it means that if you are too fast, then the cooling mechanism doesn't really work very well on you, and you will remain fast for very long times, and this is important. So, p and x are both random variables in this process, and they are both described by this joint distribution, pt, and the joint distribution satisfies this differential equation, which is called the Cramer's equation. If you want to find the marginal distribution just for the momentum, what you would do is that you will take this Cramer's equation, you will integrate over the position coordinate, and then you will get a Fokker-Planck. This will be your Fokker-Planck operator, and you can solve it and you can find the marginal distribution of the momentum relatively easy. But when you try to do a similar trick in order to find the distribution of the position, you will find that integrating over the momentum, this guy will give you a serious trouble, and we reach an equation which is extremely hard to solve. So fortunately, there is another way to look at the process. There is another way to try and find this distribution that we are interested in. And this is a picture that Ellie showed last week. Here I show you an example for one trajectory, random trajectory of the velocity with respect to time. So the velocity fluctuates randomly, and the position of the particle at time t, the final position of the particle, is determined by the area under the random trajectory. We found that it is very beneficial to study the area under this random trajectory by dissecting the velocity path into different segments that are separated by reach zero. Reach zero, and for the actually renews itself. So if we dissect the velocity trajectory into these different segments, then write down the final plus the area less, because it is important. And the total measurement time t is now the sum of tau I, and the tau i's are the durations of these constrained segments. These tau i's, you can, solving a first passage time problem, you can solve the distribution of, also it goes like, it falls off like a power law. Variance does not exist, so it means you can get segments like this. So each of these constrained segments which start and end at zero, under the excursion, and which does not end at zero is, it was also mentioned in the previous talk. And by looking at the process like this, we actually map the Langevin dynamics into a sort of coupled continuous time random walk. And now we can study it by using tools of renewal theory and the random walk, coupled continuous time random walks. So our tool of choice for finding the probability for the position of the particle will be the moment generating function. And the moment generating function written here in k space, if you take the inverse Fourier transform from k to x, you will find the probability density function. And the starting point of all of our calculations was actually to find these moments. And we actually found out that you can write down the moments of the process, the even moments. Odd moments are zero by symmetry. You can write down all the even moments of the process as a sum of two parts. One part which is related to the moments of the area under the excursion process, and the other part will be related to the moments of the area under the meander process. And we know all about it, but I didn't write it here just for making everything much more clear. So this equation here is, in fact, we found it in the long time and large x limit. These are not the exact moments. This is only the asymptotic shape of the moments at long times and large x. And this is important. This is just a flash that I will not discuss, but just to show you that we find the moments, the asymptotic shape of the moments at long times and large x by taking derivatives of this equation here. This is called the Montroll-Weiss equation, which come from renewal theory, and it basically relates the probability density in Fourier and Laplace space of the position density to the probability for one excursion having a certain area and duration for it, and one meander which has a certain area and duration for it. So by taking derivatives of this expression, we find those asymptotic moments. But this I don't have time to explain more. And Now, what happens when we use these asymptotic moments? Yeah. Yeah, so it's a good question. So the excursions here, this number of excursions that you have is actually random, okay? But you only need, in this mapping, you only need to find the distribution of one excursion having a displacement chi I and duration tau I. And this Montrol-Weiss equation tells you that if you know the distribution for one excursion and you know the distribution for one meander, you can relate this to the total distribution of the particles. But again, to solve this exactly is practically impossible. And what we do is that we just derive the asymptotic moments from this equation by taking derivatives of it and then taking the long time limit, and we find the asymptotic moments. Did I answer your question? Okay. So now, what happens when you take the asymptotic moments and you plug them in the moment generating function? Now, you know that what you are getting is not the precise moment generating function anymore because you didn't take the exact moments. What actually you get is that you obtain something that you can think of as sort of the generating function of the asymptotic moments themselves. And this is why I add the superscript A here for asymptotic. So this is the expression that you get once you plug in the asymptotic moments in the moment generating function. And please notice that I wrote the moments here in an explicit form. There is a reason for it. The point is that even though BE is now the distribution of the area under the excursion, and we know this distribution, we know how to find it, we know how to plot it, but it's a very ugly function, and to find its moments analytically is also something very hard to do. We can find all the moments, or many moments, we can find them numerically, but to find a number numerically is impossible. So the point is that there is a trick which actually generalizes this whole story a bit more. And this, with using this trick that I will now show you, we can bypass the need to find all the moments precisely, relate this PTA of K related directly only to the distribution of the step displacements. Now, even if you go back to the continuous time random walk picture, it's enough to have this distribution of the step displacements, and we will find the density that we are looking for directly from this expression, not using all the moments. What we will do is that we want to perform the summation here over M. And you can do this by using this Taylor expansion here. So this Taylor expansion is just a mathematical identity for the cosine here. We introduce this W omega, which afterwards we will take the integral of it. And when you when you use this mathematical identity, this is what you get for PTA of K, for the asymptotic moment generating function. You have the cosine here. Here you have the distribution for the step displacements, which we will keep. And now we will perform the integral over omega. And again, I remind you, what we want is to invert this thing later on in order to find the density of the particles. So, first, we used the long time asymptotic moments and large x, long time asymptotic and large x asymptotic moments to get asymptotic moment generating function. Then we want to perform the inverse Fourier transform in order to get the density. This is what this function looks after you perform the transform. You get these delta functions, they come from the inverse transform of the cosine. And when you perform the integral over omega, finally we obtain our main result, I of z, which is the infinite-covariant density of the process. Now, this equation it doesn't look well. It looks a bit intimidating maybe, but I will tell you what are the most important things in this equation. What is the most important points? First of all, I of z, the infinite-covariant density, is a limit function of the PDF. So if you take the PDF of the particle's position at the long times, it will converge to this infinite density. And this infinite density is no longer, you can see that it does not longer depend particularly on time, but rather it depends on the scaled variable where we scale x with t to the 3/2. This means that the tails of the probability distribution that we are looking for, they have this inherent scaling of t to the 3/2, and after the talk I can explain you why this tail makes sense. But you see here the probability density. If you rescale the parameter, you rescale x with respect to time to 3/2, then at the long time limit, your density will converge to this function. But this function is actually not normalizable for the range of nu, at least, that we are studying. This comes from the physical process that we are studying. So this function, despite being a limit function, a long time limit function of a properly normalized probability density, it is not normalized by itself. But this is not really a problem, and you will see why. This here, you can see results of simulations that I did by taking numerical integration of the Langevin equation. So directly from the Langevin equation, I did the simulation for different times. Different colors here mean different times. And you can see that I rescaled the probability density appropriately. So all the tails, they converge to this time-independent shape, which is given by the theoretical curve, the infinite density, in black here. Just in the bulk, really very close to the origin, you can see that there are deviations from the infinite covariant density, and you can see that with this rescaling, in the origin, the simulations, they go higher and higher and higher, because the infinite density actually at this point is divergent. But this is not a problem. Again, why is it not a problem? Because the fact is that in the bulk, the process is known to converge according to the generalized Levy central limit theorem, which I showed you in the beginning. So what we have here is a process which has heavy tails. In the bulk, it is described by the generalized Levy central limit theorem. It has a certain scaling in the bulk. If I would rescale this density in a different way, I would find convergence in the bulk to the Levy distribution. But in the tails, it has the scaling of x to the 3/2, which leads to the infinite density. Now, the Levy distribution and the infinite density, they are complementary in this case. The infinite density just describes the large fluctuations. So the Levy distribution will be responsible for the normalizability of the PDF itself. And the large fluctuation function, it will be responsible for all the higher moments of the system. So it solves the problem of the divergent moments that comes from the Levy distribution. And you can see here that for the infinite density, if you look at the small z limit, in the small z limit you have dependence only on the excursions, namely only on the steps prior to the last one, because you have many of them. And you can see this power law here, which means that this function is not integrable near zero. But if you look at the largest large fluctuations, then in this limit, the probability density, the infinite density, only depends on the meander term. BE is the distribution of the last step in the sequence. And this meander term is actually this trajectory which does not go to zero. So it means that the largest of the largest fluctuations are actually dominated by very rare events, where the particle covered the entire distance from 0 to x of t in one single jump, one huge jump. So there is strong dominance of rare events on the largest fluctuations of the system. And now this is a typical picture that you find that shows you very nicely the interplay between the Levy distribution and the infinite density. So I told you that the Levy distribution, it allows you to find the shape of the PDF at small x and the infinite density at the large fluctuations. So if you look at all the moments here, and I look at even fractional moments, fractional absolute moments and integer moments also. If you look at all the moments, you can write them as mq, which is some coefficient function, and this zeta of q is the exponent. And you can see that there is a transition where very small moments just below the second moment. Moments, they are described by the Levy distribution. But at a certain point, the Levy distribution, its moments, they are known to diverge, and the higher moments of the system, they are all described by the infinite density. This is seen from the exponent point of view. And if you look at the coefficients, you can see that it looks something like a sort of phase transition, where again, at the small moments, the coefficient is determined by the Levy distribution, and it diverges at a critical value. And the large moment is determined by the infinite density, including the. This is why the infinite density in these fat-tailed processes, it is very important, because it determines statistical properties like the variance, which are considered very, very important characteristic diffusion processes. So, to sum up, if I will have a bit more time, I will show something more on the board. To sum up, large deviation theory, that as you all know, it usually deals with fin-tailed systems, and infinite covariant density will deal with the fluctuations and the rare events of fat-tailed systems. And large deviation theory, you know that you have this rate function which allows you to calculate the fall-off of the probability, the exponential fall-off of the probability at the tails, while in the infinite density you have power law regimes of the probability density, and the large fluctuations, they will fall off according to this general shape. We use the moment generating function with asymptotic moments in order to obtain this large fluctuation function. And if you are an experimentalist, when would you suspect that such a function exists in your system is if you see this biscaling picture in your data. Then you might suspect that you have this infinite density describing the large fluctuations of your system. Right. So infinite density is actually not dependent specifically on time. I just wrote it here, but actually this means a scaling variable, z. So I wrote it here to show it explicitly, but this function is not dependent on x on time and t separately. It depends on the ratio between x to t to the beta. You can think of the central limit theorem. You have the Gaussian, which has x squared over t, and if you rescale x with the square root of t, you get invariant shape. So this is the same thing. Okay? Let's talk. And yeah, so if I have a few more minutes, I just want to tell you that the infinite density, actually, this large fluctuation functions, it actually has two types. One type is where this beta here is 0, and then this infinite density will actually be a function of only x and not time, so a true invariant function, invariant limit function. In that sense, this infinite density will be called an infinite invariant density, and it has been known to mathematicians for like 30 years now, or 20-something years. They know quite a lot about the infinite invariant measures. But the infinite covariant, where you need to rescale the parameter x with time, this is far less known, and especially from the mathematician's point of view, there is a lot to learn, we think, about these functions, and we think that they deserve much more attention. Now, to summarize, thank you for listening, and the discussion brings the light. So if you want, let's discuss afterwards. And thank you. Yeah.
Questions? For the general scaling with the alpha and beta, do you know how to get the alpha and beta from the theory, or is it something that you have to get numerically? Or?
Okay, yeah, so the point is that you can get this alpha and beta from two different directions. First of all, if you're an experimentalist, you will get the alpha and beta from these pictures. You show that your moments have biscale, and this has been found in experiments, also in biology, also in polymer experiment. It was found in experiments. And if you know this power laws here, then we have a general relation from which you can calculate alpha and beta. But if you don't know it and you only want to find alpha and beta from the theory, so basically what you can do is, if you remember the Cramer's equation that I showed you, in this Cramer's equation, you can actually, by plugging in the scaling shape of the infinite density, you can find what alpha and beta should be. So you can do rescaling arguments on the Cramer's equation as well, and this is another way to obtain this alpha and beta exponents.
Yes, yes, over here. If you take q equal 2 at the second moment, so what does it mean that the second moment grows like t to the xc? At the end will be infinite.
Sorry?
At the end, the Levy process will have an infinite second moment.
No, the second moment, so nu here has a range, which I didn't discuss, but it has a range. Nu is dependent on the parameters of the system. It depends on the size of the fluctuations in the system. And if you look at the moments, they grow in time, but this tells you how they grow in time. At infinite time, they will be infinite, but at finite time, not. Whereas the Levy distribution tells you that even at finite times, the second moment is infinite.
If you rescale the process properly, you will get some Levy process, right? And this Levy process will have infinite.
Yes, yes, precisely. The Levy process, if you rescale,
will have a certain scale invariance.
Yes, that's very important.
What is scale invariance to do with the way this momentum?
Sorry again for the question.
The way the momentum increase, what has to do with the scale of the Levy process you will get at the end?
Well, if you want to obtain the Levy process, the Levy scaling of the process, you go back to the Langevin equation and you go back to this renewal process picture. So I told you that we map the Langevin process and the area underneath it into a coupled continuous time random walk where you have displacements and you have durations, and the displacements and durations, and the displacements, they're actually dependent on the duration, because if you have a very long step, then you get a large displacement. But if you decouple the process, then you can go to this Montel-Weiss equation. By decoupling it, you will find the Levy distribution, the Levy limit. Does this answer your question?
Yes. Well, this Levy distribution will correspond to certain parameters.
It corresponds to a regime of the PDF, which is correct for small x.
It's just the Levy with a certain parameter. That
yes.
Should be.
The parameter is new. The Levy parameter is this new that I showed, which is related to the size of the fluctuations. And yes, the second moment of the Levy is divergent, but here the Levy describes a very small regime of the PDF, so it means that it describes small moments, but it does not describe the large moments. Why? Because large moments, they are dependent on the tails, on the large fluctuations. Only small moments, they are dependent on the bulk. So you can show actually in a more accurate way, which I didn't put here, you can show that the moments, they have a contribution from the Levy and they have a contribution from the infinite density, but the contribution from the Levy is completely subdominant when you look at high moments like the variance and above. But the contribution for the infinite density is, it does not contribute to the small moments, so to the zero of moments.
So you agree, you cannot determine. Suppose I don't know what the Levy process I'll get. I have information on the moments.
Yeah.
The way the moments grows. The information on the way the moment grows will not determine what is the Levy process that you get.
But you know how the moments of the Levy process,
Explained.
You know how the moments of the Levy process go. So the moments of the Levy process,
the Levy process has infinite moments.
Yeah, no, but this equation is written small and fractional moment. And this is important. Why? Because you see, the Levy distribution all its fractional moments from 0 to the new f moment here, and nu is smaller, between 1 and 2. So all the moments between 1 and 2, the fractional absolute moments, they are described by the Levy density. And only the larger moments, and basically all the relevant integer moments, they are described by the infinite density. The transition here and here, it occurs precisely on the value of nu. So you can determine what is the Levy process because you see precisely where the transition occurs. All the small moments or the fractional moments of the Levy distribution, they do exist. Only the higher moments above nu, they diverge. So by looking at the transition, you know what is the Levy process. And then you can do a stitching argument. You can stitch this guy and this guy, and basically find it's related to how you find this alpha and beta related to the question of Touchet.